All right. Good morning, everybody. It is 10 o'clock. Happy Thursday. I hope all is well with you and yours where you are today. My name is Brian, and I would like to welcome each and every one of you to the next session in the FDOT CAD Office webinar series. Today is Thursday, January 16th. It's pretty chilly up here in North Florida. I've definitely been enjoying the cooler weather, the winter weather, so to speak. There's talk about a polar vortex pushing down over the lower 48 next week, and so varying reports. There's possibly talk of snow and freezing temperatures here in Tallahassee. So we'll see. Polar vortex sounds kind of like a new soft drink special over there at 7-Eleven. So stop in today and get your own polar vortex with refillable souvenir mug. Yeah. But if it does get that cold, remember to cover and insulate your hose spigots and your exposed drain pipes. And speaking of drainage structures, yeah, that's not a really good segue there, but we have a fantastic presentation this morning from our own CAD applications training specialist and in-house drainage expert, James Worley. James is going to be talking to us today about the FDOT Connect custom drainage structures. Bottoms up. If I haven't listened to this presentation yet, but I think it's either flipping the drainage concepts upside down or the session was intended to occur after hours at a happy hour. So either way, it seems like this is going to be a can't miss discussion. So let's get right to it. Did it switch? There it goes. Apologies there. All attendees will be in listen-only mode for this webinar. Please submit any questions you have to the question dialog box. We will attempt to answer questions as we go, and time permitting may have a QA session at the end of the presentation. We'll see. It is our intention to record this presentation and post it to the CAD office website. That's the same resource in which you accessed the registration link for this webinar. This morning we had about 156 people scheduled to sign on. So as it always happens, a handful of you will experience a loss of audio at some point during the presentation or the transitions. I've been doing this a long time. So if you're new and this happens to you, please just know the quickest way to remedy the issue is to disconnect and reconnect to the webinar. Go to will record and compile and report the entire time that you're signed in, even if you have to log in and out. For this training, continuing education credit will be issued to PEs who attend the live session and who attend the session in its entirety. Certificates will be delivered to the email address in which you registered with and logged into the webinar. And with that, I am going to turn it right on over to my friend, James.
Good morning. My name is James Worley. I'm with the Florida Department of Transportation Production Support CAD Office. And this morning I will be presenting to you custom drainage structures bottoms up. Okay, let's get going. The first question I'm usually asked when I start talking about creating custom drainage structures is, why do we need custom drainage structures for all these different situations? A better way of asking that would be, why custom drainage feature definitions are needed. The reason a new drainage feature definition is needed for any variation of a structure, whether it be top and bottom, a combination of those, or a modified component, is that a feature definition has static components. The feature definition calls on specific feature symbologies that in turn call on specific element templates to make the ORD drainage structure assembly. You have to remember that these drainage structure assemblies are a new type of element and they are one element. All of these have values set to specific things like cells, templates, and so on. So a change to any of these values requires a separate set of these definitions and templates. You can see the illustration here, starting at the element template level, showing that an element template actually points to an individual cell. Once you have all of your element templates together, then you would utilize them into feature symbologies. Once those feature symbologies are made, then you can actually make the final feature definition that will be used to place your structure. All of these are necessary because, as I said, once you have defined those things in a feature definition, changing any of them will change all occurrences of that feature definition within your file. So you wouldn't want to change, say, one assembly by placing a different top or a different bottom, and then have all of the feature definitions for that particular structure in your file change. Requirements for the cells used in drainage structures. This is a very important thing to note, and it's a very important thing to understand. A combination of 2D and 3D cells are used to assemble an Open Roads Designer drainage node element. There are currently two kinds of drainage node elements used by FDOT. A standard node, which would be your inlets, manholes, ditch bottom inlets, other things like that. And then a specialty node, which would be an MES and FES, end walls, head walls, junctions, and etc. A standard node will use 3 cells: a 2D plan cell, a 3D top cell, and a 3D bottom cell. And specialty nodes will only use 2 cells: a 2D plan cell, a 3D bottom cell. The use of multiple multidimensional cells in the ORD Drainage Structure node element requires some method of aligning those cells consistently when assembling for placement. This is achieved through the use of points and lines on specific line styles. Points on line style 4 are location points and are only present in the 2D plan view cells. Points and lines on line style 3 are alignment points and alignment lines. They are used in all 2D and 3D cells to align the cells vertically and to coordinate the rotation of the cells with one another. Points on line style 5 are elevation points used in 3D top and 3D bottom cells for vertical location. Note, specialty nodes must use 2 elevation points. Connection region elements on line style 6 are used for pipe connections. Let's look at the table below. As I said, your alignment point, which is basically a point that will help align all cells horizontally, is a construction class line style 3 point. An alignment line is a construction class line style 3 line, and it coordinates the rotation of all cells with one another. A location point, which, as I said earlier, is only in the 2D plan view cell, is actually the point that you use when placing the cell in the 2D view so that you have a reference point. It is a construction class line style 4 point. Elevation point top. It is a construction class line style 5 point. It denotes the position for the top elevation in the top 3D cell, such as a cover or a ring. Elevation point for the bottom is a construction class line style 5 point that denotes the position for the bottom elevation, better known as an invert. And last but absolutely not least is the connection region. It is a construction class line style 6 shape or cone. The positions where the conduits can connect to that bottom structure are denoted by connection regions. If you do not have a properly placed connection region, you will not be able to connect pipes to the particular structure that you currently are working with. Now on to the important part. When you place a drainage structure in your current file, a few things happen in a very specific order. For a standard node, this includes the location point in the 2D plan cell is positioned at the coordinate you specify. You could specify this by an XY or a station offset, snapping to an element, or just using your cursor to identify where you want this structure placed and clicking in the 2D view. When this happens, the alignment point in the 2D plan view cell provides a horizontal position for the alignment point of the top 3D cell, and the alignment point in the top 3D cell in turn provides a horizontal location for the alignment point in the bottom 3D cell. So inside the program, it basically puts all three of those points coincident on top of one another. Then the top 3D cell alignment line rotation is matched to the rotation of the alignment line in the 2D plan cell. And the alignment line of the bottom 3D cell is aligned to match that of the alignment line of the top 3D cell. In this way, properly built cells will all end up aligning with one another's rotation properly so that they come in just as you intend them to. The top 3D cell elevation point is used to locate the top 3D cell vertically. You can use a specific value, some elevation that you arbitrarily choose, or that you know is where this structure needs to be, or you can use a surface element to have that point placed along that surface however it aligns. The bottom 3D cell elevation point is used to locate the bottom 3D cell vertically. This location will be determined by either the invert elevation of a pipe or the default minimum height of the drainage structure feature definition. Any gap that occurs between the bottom of the top 3D cell and the top of the bottom 3D cell is made up by an extrusion of the top surface of the bottom 3D cell. The result of this extrusion is that the top surface of the bottom 3D cell now extends all the way to the bottom of the top 3D cell and has no slab, so it is basically an open box. There is currently no good workaround for this, but we are hoping that in the future that will be something that we will be able to make more like the physical elements that are actually being placed in the real world. When a pipe is connected to a standard node, the invert elevation of the pipe is used to determine the elevation of the bottom 3D cell based on the location of the elevation point in the bottom 3D cell. The lowest elevation of all of the pipes that are connected to a standard node is used to determine how far down the elevation of the bottom 3D cell will be. Remembering that the standard node has a specified minimum height. This has to do with a question I get quite often. For whatever reason, someone tries to place a pipe that is shallower than the minimum depth of the structure, and they cannot get the structure to change the invert elevation of the structure to match the pipe. That's because that minimum height cannot be adjusted. You have to have at least that minimum height in order to clear the cover restrictions for the specific structure. For a specialty node, the location point of the 2D plan cell is positioned at the coordinate you specified, which could be, again, an XY value, a station offset, a point along an element, or a point at which you have just chosen arbitrarily and clicked. The alignment point in the 2D plan cell provides a horizontal position for the alignment point in the bottom 3D cell. Then, the bottom 3D cell alignment line rotation is matched to the rotation of the alignment line in the 2D plan cell. The uppermost elevation point is used to establish the vertical location of the bottom 3D cell. This is usually on or near the top of the cell. The lower elevation point is used to establish the invert elevation for the structure. This is also normally where you will find a connection region, so that when you connect pipes to these type structures, the invert of the pipe will be the invert elevation for the structure as well. Notice that there's no mention of a top 3D cell. That's because specialty nodes do not use top 3D cells. They only have bottom 3D cells. Again, the specialty nodes are things like end walls, MESs, FESs, junctions, and so forth. And now, where to start? When you're going to be using a custom feature definition to define a custom ORD structure, there are a few steps that make things a lot easier if you follow them in order. This is not the only way to do it, but this is one of the more easily followed paths. If there is a similar structure in the delivered structure list, place it where you want the new custom structure to be. If there is not one that is physically similar, find a delivered structure that is functionally similar and place it instead. A good example of that would have been, prior to us including the concrete collars, if you needed a concrete collar to connect a proposed pipe to an existing pipe, you could have used a junction cell, say a manhole, placed it where you need the collar to go, and then done the process of creating a custom structure, and then replaced the manhole with the collar you created. The next step is, if you need to physically change the shape of any of the cells, that includes 2D, 3D top, or 3D bottom, open the cell library drainage and utilities.cell. This is the replacement for our old libraries, Drain 3D cell, Utilities 3D cell, DR Plan cell, DR Plan underbar EX cell, utilities.cell, and SUDA underbar labels.cell. This was done to save having to load all of these separate individual cell libraries every time you pulled a drop down to look at the cells that were available to use for your element templates. This actually saved a lot of time for those loading, and it also ended up saving a lot of space on the hard drive, because we were able to reduce the size of the resources considerably. When all the cells you need to make the new structure are in the cell libraries, it's time to create element templates, feature symbologies, and a feature definition in your drainage work file. So this means you go and save drainage and utilities.cell so that all of the cells within it are available. Then you close that library and you go back into your drainage work file where you have the temporary structure placed and start doing the work to create your new feature definition that will allow you to place your brand new custom structure. Time to make the structure. Okay, so today we're going to have two scenarios for our examples so that you can see the simplest way of doing it and then one that is a little more complex. So the scenario one, the design calls for a curb inlet with an oversized 10 by 10 bottom box. That's a fairly simple deal because the 10 by 10 bottom box is a cell that we deliver, and it has an element template that we deliver as well. So basically it's just copy the inlet that you're going to be modifying and put a larger bottom on it. It's fairly simple. Scenario number two, however, the design calls for a curb inlet with an oversized offset 5 by 7 bottom box. The offset part of that is what's going to cause us to actually have to create a cell, which means we have to create an element template for that cell, and then we can use that element template in our feature symbology and feature definition. So here we go. Let's have some fun making some custom drainage structures. Okay, so for scenario one, the design calls for a curb inlet with an oversized 10 by 10 bottom. Well, of course, you can see this curb inlet doesn't have a 10 by 10 bottom or anything near that size. So what we'll have to do is swap out the bottom for something more appropriate. The way we're going to do this is we're going to go in here, got to start here, feature symbologies. We're going to start with the point symbology for this particular stormwater node. This is a curb, inlet 1R. We're going to copy, and then we're going to give it a new name, R. We're going to go 10 by 10. I know that was hard, but next thing we're going to do, we're going to run into the solid curb, and we're going to also copy this one. And again, we rename it. And one thing I want to stress here is when you're renaming, please make sure you leave the front of this the same as the one that it came from. The reason for that will be obvious in a moment when we're working in the feature definition. But for now, we're going to go into this feature symbology over here to where it says bottom template, and we're going to change it from the one that it is to the one that we need it to be. Wait, this is a solid, so is it showing me all of them? Nope, I think these are all the 3Ds. Yep. These are all the 3Ds. So 10 by 10. And then we go up here to the 2D, which is the point. And that's correct. They don't have a bottom on the 2D. So we're good to go there. If you did actually want to show the bottom because of it being oversized, you would actually have to make a 2D cell representing the top and the bottom, and then swap that out for what you see here in plan. And that would give you the effect of having a 2D cell that has the bottom in the cell. Alright, now we're going to go to the feature definition. You're going to go to Node, Stormwater Node, Structures, Curb, and right here. And now we are going to copy that. And again, we're going to use the same naming convention. Not trying to be creative with that. If you have it on a project, you might want to use something that identifies where it happens on the project, as well as the fact that it has a different kind of bottom. But I believe now all we do is come here, and this is why we left the names the same as the ones we were modifying. See, it appears right underneath it. If you change that whole name, you'd dig through this entire list trying to find it. And now, one more. All right, and that should be everything. Alrighty then. Now to test the theory. If I did that right, we should be able to just go here, drop this down, see the 10 by 10, and replace it. And there you have scenario 1 complete. Now, as you notice, there's no top on this box, and this doesn't look quite like what you would expect to see in the real world. In fact, it looks absolutely nothing like it. That is due to a limitation of the software, and we're hoping that we will get some way to not have to do our structures like this in the future. But this is a inlet with a 10 by 10 bottom. Alright, we're going to start scenario number 2. Scenario number 2 called for a curb inlet with an oversized and offset 5 by 7 bottom. Well, as you can see, we have our wonderful curb inlet with its round bottom, which is definitely not what we're looking for. The thing that is different than from scenario 1 is the fact that we don't have a 5x7 offset box for you to use. So you're going to have to create one if you want to be able to do that. So the way you do that is you go into the Drainage and Utilities cell library. You find the original, which is 5x7, that you're going to be using. Make sure you're in the 3D file. And you're going to need to make a copy of that. And we're going to make this one easy enough to tell. Alright, now that we are in that cell, you don't want to change the original cell. You want to change your copy. I can close this and go about my work. Now, one of the things I like to do, because, you can do a lot of measuring ahead of time and figure out how far you need to move things, or you can just use simpler tools. Which is a reference. And I'm going to reference the file that I'm currently in. So that would be here. Need to change what I'm looking for to see cells. And click on the right one. Open. And now let's find our wonderful structure that we need. It should be right down here. That one right there. And when I say OK, it should come in. Now, I'm going to close that for now, but you see how it aligns, and you see how these points are all coincident. The ones in that cell, the ones in this cell, and if I put the 2D in here, those points and that rotation line would be coincident as well in the 2D cell. So that's why I stress always making sure you don't move any of these things, whether it's the line or the points, when you're manipulating cells. Maybe I should leave this little booger open so that I can turn that on and off. I'm going to move it off the screen right this second, though. Not enough room for everything. But right now, what we're going to do is figure out how far we can move this so that it pokes out further towards the back side of our structure. In fact, we're going to do it as far as we can. So, the easiest way to do that is to first turn that off. Then I'm going to grab a hold of these guys so that I have all of my points that have to stay where they're at. I'm going to hold down Control and grab the rest of everything else, which will let go of the ones that I just had a hold of and basically select literally everything else. Now I'm going to come up. Where are my tools? Where are my tools? Let's go into drawing. That'll be an easier place to find standard tools. And we're going to move. And I'm going to go ahead and grab this surface right here. I'm going to click my enter key to make it so that it can only move in the direction I want it to. Then I'm going to turn the display of this back on. And right there, you see that line matches up. Well, it did. Let's see if I can get a hold of it. Yep, there it is. That's my outer circle of the throat of our structure. So if I click there, that moves that box over there as far as it can go. Now our cell is ready. The next thing I need to do is make sure that I detach the reference that I have. And now our bottom structure is ready to be used as an offset bottom. So we save this and exit that version. All right. Now we have the fun of we need, excuse me, sorry, stop it. We need to make an element template. Element templates are pretty easy. There's all of the ones that we have, drainage bottoms that we have in here right now. So let's see, where are my drainage and utilities? Drainage bottoms, and the one I'm going to be manipulating, 5x7. Making sure that I'm getting the 3D. It doesn't look like I am, but maybe this is, even though it, yes, it is. See, you can tell by the little 3D there on the end of the name. Okay, so what I'm going to do is take and copy that, come up here, and paste that. I now have 5x7, but I don't want 5x7. I want 5x7 offset. All right. Now it should be able to go over here and find my offset. Or I may have to restart. Looks like it. Okay, that's not a problem. I'll be right back. Okay, after a quick restart, we're still trying to get the 5x7 offset bottom element template set up. So the active cell, as you remember, I did this drop down and it looked like this with no offset. But after a restart, there's my offset. And now I have that as an element template in this file. Alrighty then. Close that. Now in order to make this happen, we're going to have to do the same thing that we did in the first scenario. We're going to have to come into the symbologies for both point and solid. We're going to have to make a copy of this 1R that we're starting with. Five by 7 offset. 5x7 offset. All right. And on our solid, we'll need to change this bottom from what we see there to what we see here. All right, that's everything for the solid. Now for our 2D, guess what? There's nothing to change. So we can now go to the feature definition. Once you're in your feature definition, drill down, get the curb, 1R. I really hate when it does that. Copy. Rename. Now all we have to do is change these. Come on. It does try to be difficult sometimes. Here's our 5x7 offset. Here's our 5x7 offset. We now have a solid feature and a point feature symbology set correctly, so that now we can go back to there and come into our file. Oh, don't grab that little booger. There we go. Now then. And now we have a 5x7 offset bottom. Again, my name is James Worley, and I would like to thank you for attending my presentation of custom drainage structures bottoms up. I hope you enjoyed the presentation, and I hope you got something out of it. My contact information will remain on the screen for a bit, so that if you want to take a picture of it so that you can contact me later, that would be great. I look forward to hearing from some of you with questions and possibly some suggestions to make things better. Hope you have a wonderful day. Enjoy.
All right there. Thank you very much, James. Was a great presentation. I especially liked at the end when you said, I look forward to hearing from some of you. Well, everybody, that was it. James, I want to thank you for your time and efforts in creating that presentation today. We will be bringing you the next webinar on Thursday, January 30th and that'll be brought to you or brought to us by Randy Roberts and Mike Rocca when they discuss FDOT Civil 3D 2025 drainage workflows. So we're kind of going along with the same topics there. You don't want to miss out on that one. Before I turn it back over to James, I just want to say I truly hope everybody has a great rest of the week and a fantastic weekend. Stay warm. James, my friend, if you are with us, the floor is going to be yours. Please go ahead with any closing comments. Mention some of the questions if you would like. Say your goodbyes, and then we will close it on out. But we will be posting the Q&A PDF to the website where we put the videos as well. So I see, James, you're online, but you're muted out.
Can you hear me now?
I can hear you now, sir. There you go.
Okay. All right. Yeah, I tried to get all the questions answered. I think I've got one still hanging out there about structure bottoms not following standard minimum sump depth. Currently, that is actually being worked on for our later release. Adding sump in there, the way they were originally done, the elevation point that located the incoming and outgoing inverts in the bottom of the bottom cell were actually, that point was actually placed directly on the surface of the bottom of the box, which is not exactly correct. Found that out after it was released and after it was done, so it's a change that's got to be made. Something that we are working on, or I am working on. So sorry about that, but it's easy enough to fix, and it's just the movement of that one little point. So seeing the questions that I have answered, I hope everybody enjoyed the presentation. And like I said before, I hope you got something out of it. This is a process that can be used both in the current release, the newest, with the single cell library, or it can be used in the older software that had the original Drain 3D and DR Plan cell libraries. You just have to jump back and forth between the two when you're doing the 2D and the 3D for those cells. I don't really know of anything else that I can add. I hope you guys tune into the next one. And that's basically everything from me, Brian.
All right, well said. I appreciate you, sir. Just like you know, the video is going to be posted on the website, just like all the rest of them, the QA PDF as well. And we hope everybody has a fantastic day.